Thanks, everyone. I hope you're enjoying the start of this meeting. Sounds very interesting. Sorry I couldn't join you there, but I'm very, very happy to be able to share with you some of cool MeerKAT results and tell you a little bit more about MeerKAT. So I understand that, well, there's a variety of people in the audience, but many of you are relatively young, maybe MSc students, etc. Maybe a few of you have seen MeerKAT data, but maybe not too many. And what I want to leave you with the impression of today, hopefully, if nothing else, apart from a bunch of, pretty pictures, is that MeerKAT is an incredibly awesome instrument. I mean, MeerKAT is, for some things now, the world's best research instrument. And it was fully developed in South Africa, essentially by South Africans, most of them. And it's right here in South Africa, in the Northern Cape. And it's working, as you'll see. And it's there for the taking, for great ideas. So some of you, I hope, will be doing your master's thesis, PhD thesis with MeerKAT data, and then going on to postdoc, some of you, and carrying on as astronomers. And it's a really, really wonderful instrument. Okay, so let's start. And by the way, I can't really see, my screen and stuff. I can't see you guys. I can see Ben over there, but so I will be very happy to address any questions at the end, but I suggest let me just go through the slides. So here it is, a beautiful picture of MeerKAT in the Karoo, 64 dishes, or however many you can count. And you see two little, little thumbprints, two sort of small images of MeerKAT. Now, one of them is of an extragalactic object, and one of them is of an object in our own galaxy, and you'll find out during the talk which one is which. So MeerKAT is the SKA square kilometer array precursor, South African square kilometer array precursor telescope up in the Northern Cape, made up of 64 dishes, about 13.5 meters in diameter, and they're separated by up to 8 kilometers, right? And they have receivers in 3 different bands, as noted there. And these are just some of the pictures from construction days. And on the bottom right, you see this building that's both a power station that keeps MeerKAT operating regardless of what power is coming in from Eskom, and also contains things like the very important correlator and other, the time and frequency reference subsystem that has masers, atomic clocks, etc. This is an incredibly complex machine. But effectively, all the data kind of goes in there first and then gets sent to Cape Town. I'll get back to that. So what's the bigger picture context? Why do we have a MeerKAT? Well, because there's this international telescope called the SKA. Well, it's an observatory that has 2 telescopes. So 2 telescopes are now being built, one in Australia, dealing with the low frequency end of the radio spectrum. And then the other one built in South Africa, the SKA Mid telescope, covering higher frequencies. And MeerKAT will form the core of this international SKA telescope. So many more dishes, bigger dishes will be added to MeerKAT. But MeerKAT in its own right is already, like I said, for some things, the best research instrument in the world. And I'd like to start the pretty images with this one. So this image was shown at the inauguration of MeerKAT, which is, about 4.5 years ago now, July of 2018. And it's a super pretty image, and it's as it says, this is not a lie. This is the clearest image ever made of the center of our own galaxy at radio wavelengths of this nature. Very high fidelity image. Why do we care about radio waves, the galactic center, etc.? Well, ordinary light cannot penetrate all the dust between us and the galactic center, 25,000 light years away. So we can learn a lot from radio waves, also X-rays, some infrared radiation, but for radio waves, this is the best image ever made. And it was made right then and there at the inauguration. We had only gotten the telescope working a few months before this. So it's really quite stunning that this was done so quick. And as you see on the bottom right, there are 2 very important people. They're presidents of 2 countries, including South Africa, are very excited standing in front of a banner of that image. But of course, this is not science. So you might think, okay, cool, it's a pretty image, but does it really do science? Does this lead to cool science? Yes, it does. Just last week, the Royal Astronomical Society of London, one of the oldest such societies in the world, awarded this very prestigious award to the MeerKAT team. They only award one such award once a year. And this year, we got it. We, the royal we, as it were, of the MeerKAT team, includes Oleg, and includes Ben, and includes really hundreds of other people around the world, but mainly in South Africa, that are doing now, well, the science with MeerKAT. So science is being done within South Africa and also across the world, and I'll show you some examples. So this is for real. This is really one of the world's leading research instruments. Of course, it didn't come to pass just quickly at all. As you can see, this is in one slide a brief history of MeerKAT. And at the top left, you can see the project that eventually led to MeerKAT started 20 years ago. In fact, we're celebrating this year the 20th anniversary. And then 15 years later, as you can see on the bottom right, MeerKAT was actually inaugurated. And along the way, all sorts of engineering, development work was done. This sort of prototype engineering demonstrator called CAT7 was inaugurated, was built. I mean, all sorts of things had to be done before, well, one could reach this world-class research instrument. So it's a long story. To give you some numbers, if you haven't heard about them before, I mean, you may have heard of the VLA. If you haven't, you will know about it soon if you continue in radio astronomy. It's still, for many things, the gold standard of, of these types of telescopes for many things, but not all things. MeerKAT now is it for some things. And here, those antennas on VLA, I mean, there's 27 of them, but each of them is 25 meters in diameter, which is, of course, much larger than a MeerKAT antenna, which is 13.5 meters, as I told you. And yet, never mind about the details and the units and whatever, the point is across this band that you see here, which is the so-called MeerKAT L band from 900 to 1700 megahertz, one MeerKAT dish is just as sensitive as one VLA dish. I mean, how can that be? Theirs are much, much, much bigger. Well, because ours are more modern, are built with excellent technology. In this case, the radio receivers are the best in the world, developed in South Africa by the South African company. That's one example. The design of the dishes is very different. It's the so-called offset Gregorian. It's an unblocked aperture. The radio waves come. They don't really strike any sort of strut supporting legs, which can mess up various things in your radio images and so on. And they basically just hit the radio receivers after following a very clean path. Right? So this gives you this. So each dish is really more efficient. Effectively, it's almost like a bigger dish compared to other types of design telescopes. So, and this is just to show you, if you haven't already heard, I suspect you've already heard about UV coverage and baseline distributions and so on. So we have 64 dishes. So if you do the numbers, right, you have 64 times 63 divided by 2 individual baseline pairs, combinations of 2 dishes. So that's 2016. And that's a huge number in the context of these telescopes around the world. And that ultimately leads you to good image fidelity, if everything else is working well. And after you do a lot of work, a lot of data processing, like Ben and Oleg and others will tell you about and this week, or you already know. But this gives you a sense of what is the baseline distribution for MeerKAT. Right, another thing I should mention here, because if you work with MeerKAT data, you will be dealing with a lot of data. So never mind the details of this slide. You can, if you understand, that's fine. But basically, huge amounts of data are coming off our 64 antennas. It's 2.2 terabits per second. That's how much data is actually being collected at the antennas. And then they go to that central building that I've already shown you, this so-called correlator. All sorts of mathematical operations get done on those data. The data volume gets reduced, in this case to only 200 gigabits per second, and then more things get done, and calibration and so on, and averaging and whatnot. But in the end, you still end up, for a typical observation of a few hours, you still end up with quite large data sets of many terabytes in the archive in Cape Town, from which you download your data to then analyze and to eventually make pretty images and so on, like you'll see in this talk. So it is, it's a data machine, and you're basically doing data science in addition to astronomy when you're dealing with MeerKAT. So just schematically, very schematic, right? This is a cartoon of what happens. So the radio waves come to each of the 64 dishes in the Karoo. They get detected at the dish, digitized into the ones and zeros. Then they go through fiber optic lines, underground fiber optic lines, to our central building in the Karoo, the so-called Karoo Array Processor building. And then eventually they get brought to Cape Town, to the archive, which doesn't really look like this. It's fancier, but in any case, that's schematic, and it's all controlled by the control room in Cape Town and the operators and so on that are controlling this whole thing. Of course, this is really about people, not cartoons, and so here are some of the colleagues in the Karoo on the upper left, in Cape Town, and the other 3 slides that do and have done all of this remarkable work. Now, to give you a sense, fly over to site, so 600 kilometers to the northeast of Cape Town, more or less, you will find our site in the Karoo. The nearest town is about 90 kilometers away, Carnarvon, and Ben is from that area, so he knows it very well. Yeah, here these little balls indicate the positions of each of the 64 antennas of MeerKAT. And there's the Cat 7 telescope that is now mothballed. It served its purpose wonderfully to teach us what to do and what not to do while building MeerKAT. I mean, without Cat 7, there would be no MeerKAT, or as good a MeerKAT in any case. And there you get a sense of the scale. So Cat 7, the dishes are separated at most by about 200 meters, whereas for MeerKAT, as I said, it's about 8 kilometers. Right. So now getting to the science program, what has been happening? Well, Jesus, that's 2010 there. It actually started in 2009 with a call for proposals for the international community. So that's, what, 14 years ago now. And then many, many things happen. As you can see there, maybe an important point to focus on is that about 2/3 of the telescope time in the first 5 years of operation for each of these projects is to be used by the so-called large survey projects, or LSPs. I'll show you next what type of science areas they cover. So 2/3 of the telescope time was pre-allocated as of, well, many years ago, especially since 2017. But then the remaining 1/3, roughly speaking, most of it, is awarded through these periodic so-called open time calls. And now we are on a schedule. So now every March coming well, in 2 months' time, less than 2 months' time, we'll issue the next call for proposals, the 4th call for proposals. Anyone from around the world can submit their proposals. Maybe some of you guys, together with your supervisors, etc., will write proposals to observe whatever you'd like to observe. And then there's a very large oversubscription. It's a very in-demand telescope. There will be reviews. And then the best projects get selected. And then we observe. And then our colleagues get the data and start doing things you learn about this week. And eventually do the science and do the images that you'll see in this talk. So here are the areas covered by these so-called large survey projects. There's a variety of pulsar timing, pulsar searching, variety of studies of H1, neutral hydrogen, the most plentiful element in the universe, as well as continuum surveys, absorption line survey, and this explosive/accreting transient studies, a project called ThunderCat. So it's a wide variety of science areas. And now let me give you, with lots of pretty images in general, a sense of the first papers that have come out. So this was the very first paper that came out based on the full MeerKAT array in September of 2019, based on the same data set that we had collected for that inauguration image that you saw with the 2 presidents, which was presented a bit over a year earlier. So that gives you a sense. It took more than a year for some very hardworking, clever people to work on those data to eventually produce this paper. And you see here this bubble, or maybe if you don't know what you're looking at, I mean, that's the galactic center diagonally across, but maybe it's better seen here. So that it has horizontally across, that's the galactic plane, the plane of our galaxy, the Milky Way. And then vertically, perpendicular to it, you see this sort of bipolar bubble structure, which was not known. Parts of it, the brighter parts of it were known, but it hadn't been realized that this is a coherent structure. And before MeerKAT. Another very interesting thing is you see all sorts of filaments here, these very narrow filaments, which turns out they don't really exist that we know of anywhere else in the galaxy. And there's hundreds of them right around here. And it hadn't been realized, which I highlight here in yellow, it hadn't been realized until this data, this image, this paper, that these filaments seem to be, well, as you can see, at least in projection, pretty much bounded by this bubble structure. So our inference from this, our conclusion is that whatever created this bubble, huge bubble, more than 1,400 light years across, some big explosion or some explosive event in any case, very energetic event a few million years ago, it also generated the electrons or accelerated the electrons that are now causing this synchrotron emission that's leading to all these filaments, with some local magnetic fields. So that was, I think, a very important discovery, and it was right there on the first paper with MeerKAT. Then more early papers. This one, every dot you see here, pretty much, almost every dot you see here, there's tens of thousands of them, are like a galaxy like our own, the Milky Way, except halfway across the universe. Okay, so they're very, very faint in the radio. But MeerKAT, this is the most sensitive image ever made at radio wavelengths that's sensitive to these types of galaxies like our own, but halfway, long time ago, far away, halfway across the universe. And this is remarkable what you can do with this. You can constrain the so-called star formation history of the universe. Stars are being formed even in a galaxy like our own, but at a certain rate per year. But that rate changes over time, over cosmic time. And that's very important to know, to understand how the galaxies come to be and form in the way they are now, and stars form at what rate, why, how. Well, MeerKAT, this image, the data underlying this image, and then work by other people as here, have already advanced our understanding of this field. Here are other examples, again, beautiful images on the right. The so-called X-shaped galaxy, it doesn't look like very X-shaped to you, probably. It's more like two boomerangs, but back to back. But if you, like me, had glasses, spectacles, and you took them off, very, very fuzzy, it would kind of look X-like shape. And there were various theories for why these kind of galaxies, there are a few of them known. How do they evolve? How do they form? Are there two black holes at the center? Is one black hole turning, or is a black hole turning off, then turning back on in a different direction and spewing, synchrotron emission along that new axis? There are many, many theories, as I said. For this galaxy, at least, clearly, the so-called hydrodynamic backflow model, which is explained in cartoon shape by this little inset here from a paper from 30 years ago or so. This is the correct model. So again, very pretty image, but clearly what we're trying to do here is learn about things like galaxy formation, etc. Then on the lower left, Mpati Ramatsoku, when she was either a student or a postdoc, I forget now, South African, she found in this data, this is otherwise a relatively normal radio galaxy. At the core, you have a black hole, spews out jets, you have these big lobes on the side. But what's unique about this image is that there's these filaments, these threads below the center that connect both lobes, which are otherwise, well, hundreds or hundreds of thousands or even millions of light years away from each other. So what are these filaments doing? What causes them? How is this happening? It's still very much an open question, but MeerKAT started showing these types of phenomena, which now we've seen in, let's say, a half dozen galaxies or of that order that I know of. There's probably many more in data that is not yet published. But yeah, we've been seeing this with MeerKAT, so very exciting. So here's another example altogether, which is hydrogen. MeerKAT, as I noted in one of the earlier slides, was actually optimized. The way it was built, the distribution of the base of the baselines of where you stick all those 64 dishes was optimized to be able to detect this, sort of low surface brightness features and in this hydrogen that we say is very important, of course, to understand how galaxies form and evolve. And this was the first paper that described in a very famous galaxy the detection in blue. These are blue clouds of hydrogen. Some of these were known already. This doesn't tell you how bright they are, but the brighter ones were already known, but many of the others were not. And so MeerKAT discovered about 14 times more hydrogen than previously known in this galaxy. And it kind of solves the problem that what people thought they knew about this galaxy, that's a result of the merger of two galaxies, but the hydrogen was missing. Well, not missing any longer after MeerKAT came into the picture. This is yet another paper, the first paper using a so-called different mode of our correlator. All the papers so far had used the so-called 4,000 channel mode of the correlator. You stick 4,000 frequency channels, you slice the full bandwidth of the receiver into 4,000 frequency channels. With this mode, you slice it into 32,000 channels, which is great for certain studies like this. You have higher frequency and velocity resolution. On the other hand, you get a lot more data, which is harder to analyze, and so on. And maybe I won't go into detail. You'll learn this week if you don't know already. But with MeerKAT, you can do, well, other telescopes of this sort as well. You can weigh your data in different ways, and then you either get more sensitivity to low surface brightness stuff, like on the upper right here, you detect fainter hydrogen, or on the upper left, you can have higher angular resolution images, although with less sensitivity. And you can do that with the same exact data set. It's just the way you play around with the data. So as the writer of this paper wrote, the PI Erwin de Blok, the principal investigator of one of our large survey projects, said this is exquisite imaging data. Really very happy. This was the first paper. I won't go in details. The first paper using a different receiver, the so-called UHF receiver at lower frequencies, that we inaugurated later, that we commissioned later. But this was the very first paper that came out on the basis of absorption. And then we also have pulsars. We do, this is not imaging observations now, so it doesn't look as pretty unless you're a pulsar person. But it's very pretty because actually, in this paper, our colleagues demonstrated that with MeerKAT, they could time a pulsar, basically predict and measure the arrival times of the pulses of this rotating neutron star, hundreds or thousands of light years away. They could measure it with a precision of 4 nanoseconds within 1 hour, which is astounding, the world record. And for that, you don't just need a very sensitive telescope like MeerKAT, very sensitive, all those dishes, those fantastic receivers, etc. But you need everything working properly, the so-called time and frequency reference, the masers. You need to basically measure every little delay in your instrument from the time the radio waves hit your antenna. You need to figure it out because, of course, the dishes are all at a different distance from the center, from the correlator. There's all sorts of variations you have to take into account. And only then, after all of that is done properly, do you get to this kind of ridiculously good timing precision, which then leads you to be able to do interesting science, to detect gravitational waves, and to sort of constrain theories of gravitation, like Einstein's theory of relativity, and so on. So yeah, so this is great stuff. This is a totally different example. This is, I believe, Laura Dreesen. At the time, I think she was a student. She did, and now I believe she's a postdoc, possibly. Apologies if I'm wrong. She made the first discovery of a transient with MeerKAT. So at the bottom, never mind, that's X-ray and ultraviolet data from a spacecraft. But at the top, you see the same field of view observed with MeerKAT twice, once in October 2018, once in January 2019. In one instance, you see a dot source. In the other, you don't. So it turns out this seems to be a chromospherically active binary star. I mean, never mind the details, you can read the paper, but it was the very first time. This was not the purpose of this science, of these observations, right? So MeerKAT, one thing I haven't mentioned, is compared to many other telescopes, it has a large field of view because the dishes are smaller, so you can actually see quite a bit of the sky at once. And these guys, the Thundercat team, they're often pointing at, well, they're interested in one known object at the center of the field of view where they point, but then they have a very large area where there's thousands of sources. And since they look at these objects of interest to them every week, well, after a year, they have about 50 snapshots, like a slow moving movie, where the frames move once per week. And then you can find out this variability. So again, I'm giving you all sorts of range of science and types of observations you can do with MeerKAT. And I'm sure some of you will hopefully end up doing some things, others other things, will come up with new ideas. So still speaking of transients and variables, here's a movie that Oleg made a while back now. But this is based on a conjunction, I don't know if you remember, in late, basically Christmas Day or so, 2020, a bit over 2 years ago, Jupiter and Saturn came really close together on the sky, the closest they'll be in hundreds of years or something, I think. So very close on the sky. You could see it with the naked eye. And we decided to just point MeerKAT at it and see. So I won't go into the details of this very pretty movie. You can ask Oleg later in the week. But basically, this funny looking thing on the bottom right and in the center and lower left, that's Jupiter. Jupiter and Io, it's moon Io, and there's this, there's a lot of the radiation belts because of its moon Io, but never mind. And it's rotating every 10 hours, which is more or less the time that it took to do this observation. So you actually see Jupiter wobbling over 10 hours. It's like a slow-moving pulsar that rotates every 10 hours in a sense. But then on the lower left, you can see Saturn. That's the little dot above Jupiter that approaches it within the observation, a little close. This was near the closest approach. You see galaxies in the far-off universe, these funny-looking, dumbbell-shaped things. And then you see a transient there in the circle. So something that wasn't there most of the time, but in this movie with 15-minute, I think, frames, you can see it in one or two of those frames. So Oleg and his colleagues are working on this for publication. So this is a very interesting result as well. And then there's other things. So I don't spend the whole day here. That we had Kenda Knowles, who, well, she's a South African young researcher. She was once a student like you, and with, I suspect, probably bursaries from Soreo, and then a postdoc and a researcher at Rhodes University. She led the publication of this amazing data set about a year ago, I think, which is clusters of galaxies. So galaxies, they don't always live in isolation in the universe. Some of them are in these little groups of galaxies, and others are in these bigger, more dense clusters, enormous structures. And then they interact with each other. There's a lot of gas there that heats up. There's collisions. It emits X-rays when it's hot, like on the right panel here. The contours are from Chandra, I think, Chandra or XMM image up in space. Beautiful X-ray satellites. The orange data and this black and white image in the middle are all MeerKAT data of these clusters of galaxies, and some interesting interacting galaxies here on the left. So this is just a vast amount of data. That this is one of those good examples. So this paper was published. It summarizes the observations we did on 115, I think it is, galaxy clusters throughout the universe. And then the data was also released. So in this case, if you don't want to go, if you have an interesting idea that you could work on the basis of this data, you don't have to go to the raw data, the so-called visibilities, and then spend a year or more making images. The images, depending on what you want to do, may already be there, and you can just download them from the Soreo archive, and then you more quickly start doing your science, if this is your kind of thing. Very nice data set. Then another one we're working on is the galactic plane. I mean, the Milky Way. That's an obvious one. There's only one of those in our universe, in our galaxy. Many interesting things happen there, supernova remnants, etc., star-forming regions, and we observed this a while back. And just to give you a sense again of the MeerKAT improvements over previous telescopes. So this image is a 3 by 3 degree segment of our entire survey of the galactic plane. And I want you to focus on this square up top here. I'm circling a thing that's a supernova remnant, and now I'm going to show you a zoom in on that. So that's on the left. And on the right, you see the best previous image, I mean, prior to MeerKAT, with this other older telescope in Australia. And you can hardly tell that these are actually the same thing. I mean, it's stunning what MeerKAT can do on the left. And this is, again, part of the galactic plane survey. There's these threads all over the place. We don't really know very well what they are. That's, I think, work in progress. Then there's some bizarre objects like this one. We don't know. Our best guess is that it might be a pulsar wind nebula. So the synchrotron nebula generated by a pulsar at the center. The only problem is we don't really see any pulsar at the center. So, and it looks very bizarre with all these twisted filament structures, etc. If you're interested, you can read this paper that was published last year. And just to give you another, I think, really cool image of, this is of a supernova remnant. A known supernova remnant. On the right, you see the image done with the VLA and the compact array in Australia together. And on the left, you see this beautiful, almost three-dimensional, jumps out of the page of the screen at you, this image of the same supernova remnant observed with MeerKAT. And that quote is by this guy, David Helfand, who's a great astronomer in the US, in New York. And also he's a chef. He's an extremely good cook. And he said that to him, this looked like a perfectly cooked pizza crust, this MeerKAT image of this supernova remnant. So that's pretty cool other image. Then we go to the galactic center. going back to the beginning, where I showed you that original image from the inauguration of the telescope with the two presidents, etc. But that was 2018, so that was PR, good PR. I mean, beautiful image, but that was not science. But then Ian Haywood here, seen in front of the image that he generated from the data. This is on the day of the inauguration, but then what, 3.5 years later or so, we finally produced a paper and a scientific article on the basis of all the discoveries and the data more properly presented from that original observation. And here you see some of these images. So the top is the so-called total intensity image. That's what you see when you average across all the wavelengths that you have in your band, all the frequencies of the band. It doesn't make any distinction as to whether it's 1000 megahertz or 1400 megahertz. It's just kind of what you see, monochromatic in a sense. But then below it is the exact same field of view from the exact same data, except now effectively, well, you're plotting what's called the spectral index. So you're taking into account, are things brighter at the lower frequencies or at the higher frequencies, and how does that vary, and so on. And never mind the details, but evidently, immediately you see this little structure at the center that's different. So that's actually called the mini spiral that is surrounding the very, very massive black hole at the very center of our galaxy. I mean, this was a known structure, but the point of these images on the right, similar thing except for a supernova remnant in that same data set with a pulsar wind nebula at the center that has a different spectral index, etc. But it tells you that the spectral index business is quite powerful in allowing you to disentangle what's going on physically, in the data with these objects, to learn more about the physics, the astrophysics. So this is an incredibly, incredibly rich data set, which had a lot of play once we put that paper out, a press release. So here it was in the New York Times. They decided this was a very nice result, an image, and so on. So there you go. So it had that kind of play. And here you had a different one. So on the right, this is the same data set. All these colors are representing that spectral index that I referred to earlier, but now for the entire data that we released in this paper about a year ago or so. So this was colored and this was done by a professional astronomer who's also an outreach officer at ESO, at the European Southern Observatory, Juan Carlos Munoz. So he shared this with us, and it's really cool. And because he works for ESO, he also put it there together with one of the VLT telescopes, the very large telescopes, and that's to scale, I'm told. So you can see them, this is a few degrees across the MeerKAT image, and you can see it there in context of the beautiful optical image, which, again, to remind you, it's beautiful, but you cannot actually see into the galactic center with these optical images, but here you can with MeerKAT. So that's wonderful. So now, just to summarize, maybe the big picture, well, not big picture, actually contains lots of details, but comprehensive, let's say. The current status in some dimensions of the MeerKAT telescope. So all of the large survey projects that, in a sense, MeerKAT was originally built specifically to address. I mean, some of the distribution of the baselines of the dishes, etc., were in part implemented just that way in order to be optimal for certain science that's captured in these large survey projects. So those are all in the way. I mean, they started between 2018 and 2020, thereabouts, as we develop new capabilities. We have this so-called director's discretionary time. That means that people can write short proposals. Something happens in the night sky, goes bang, whatever, that you couldn't have foreseen the previous year when there was a deadline for a proposal. You can write a little proposal, and that we have that ability. And these so-called open time programs. We are doing, as I hope I've shown you, both imaging data, lots of it, with various modes of the correlated to do different kinds of science, pulsar timing and pulsar searching, so-called commensal data. I mean, I've already shown you type of commensal science in the sense that when I showed you that detection of the first transient, that was not the original purpose of the data, but there you are. You got some science for free, in quotes, for free after some clever students, postdocs, etc., did some work. Obviously, it doesn't just fall out of the sky. No pun intended. But we have other instruments that work in parallel with the primary purpose of an observation. Let's say someone is pointing at a galaxy because they want to study something, they want to do imaging. But then we have this MeerKAT user-supplied equipment led out of the University of Manchester in the UK to detect transients that may just be happening, going on and off, very quickly in the field of view. Then recently we've gotten this new equipment for SETI, Search for Extraterrestrial Intelligence, that's led out of by our colleagues at the University of California, Berkeley, and others, in South Africa, etc. They built all this equipment to basically capture data in parallel, wherever we're pointing to a galaxy or something. They're searching with a lot of electronics, a lot of computers for particular signals from extraterrestrial intelligence, technologies beyond Earth. And the MeerKAT telescope is an optical telescope, small 60 centimeter or so diameter optical telescope that's in Sutherland on the side of the South African Astronomical Observatory, our sister institution. And there was a purpose-built telescope to track MeerKAT. So every night, at night, obviously, because it's an optical telescope, wherever MeerKAT is pointing, typically MeerKAT is pointing at the same place with the same field of view, with an excellent camera, etc. And so you can sometimes find, transients or interesting things and then you can immediately correlate the radio signals with the optical signals, etc. So that's a very, very, very interesting project. As I said, we have the UHF receiver, which is, the most used receiver is still the L band, but UHF is next, and S band at the higher frequencies, set of receivers built by our colleagues in Germany, Max Planck Institute for Radio Astronomy in Bonn. That actually, essentially, it's available for science now. I think the very first observations have either started or about to start, and we expect great things out of that new capability. And, we still hope to develop some other new capabilities in the coming years. Lots and lots always still to understand about this very complex instrument. And just FYI, for those of you who are interested, talk to your supervisors, etc., colleagues. Like I said, in March, in a couple of months, we'll issue the next call for proposals. But in the meantime, you don't always need to get new data to do new science. We have huge amounts of data, petabytes worth of data, if you care about the number of bytes, petabytes worth of data that are no longer proprietary. That is, they're publicly available. Not only that, but we have data releases, which I'll mention in one of the last couple of slides, to help you get your science faster, if that's the kind of science you're interested in. We now have, the community has generated, as of yesterday, 178 refereed publications in the literature that contain MeerKAT data, and you can go read all about them in this little URL if you're interested. And eventually we're going to have this so-called MeerKAT extension, which is to add new dishes, SKA design dishes on longer baselines, roughly twice as long, to MeerKAT. And eventually we'll have the SKA. So this is just a screenshot of what happens if you go to that MeerKAT so-called ADS library, and you will find all the details. You can have a jumping point up to the 178 papers as of yesterday that contain MeerKAT data. There's also this tool, this app on our website at Soreo, where you can find out what was observed. This was a screenshot I took yesterday. So by default, it tells you data that was collected in the past week. You can see here from the 9th to the 15th of January. And you can see at the top there, this project is one of the large survey projects. I've already mentioned it. Until now, since the beginning, it has collected 1,176 hours, but in the past week, there were 17 hours collected. And that one doesn't yet have publications, but down here, you can see some other projects that have a lot of publications. And you could, if you were looking at this live, you could click on them. That would be another jump off point to go to the publications and so on. So it's quite interesting, this thing. I encourage you to use it. And I mentioned the data releases. So this is an example. You get more pretty pictures, like on the right, that's a fantastic picture of a radio galaxy. We call Fenneroff-Riley type 1 object that is really, really a stunning image that MeerKAT made. And you can read the paper about what we learned from those observations. But the reason for mentioning it here, apart from being a pretty picture, is also for the same reason that I have the other two data sets on the left. So these are, there were papers published in the literature associated with these data, but then the authors put all their images, and I don't mean a JPEG or a PNG file, I mean so-called FITS images you can actually quantitatively do work with, scientific work. They are there off these, well, these URLs that we have here, but we have a web page that lists all of these. And so on the top left, for instance, if you care about, there's this project, this atlas of almost 300 galaxies that were selected according to very specific criteria, of course. But the images for those 300 galaxies are available off our website, the FITS files for those. And anyone, whether it's a student, whether it's a for fun project, or whether you have some scientific idea, you just go grab it and do your thing. On the bottom left, it's a very different story. Deep observations, again, many of these dots, thousands of dots, galaxies like our own in the distant universe. Again, the data, it's not only that the raw data are public, these data sets, the images, the FITS files, spectral cubes as relevant, they're all available publicly, okay? So, my last slide. That's MeerKAT. I mentioned MeerKAT extension, and that's happening right now. Here are some foundations late last year. Oh, wait, sorry, no, that's wrong. That's already more than a year ago. Huh. Time flies. In any case, yeah, so these are some of the foundations for those 16 dishes that we hope to add to MeerKAT, but they're not MeerKAT dishes. They are these SK type design dishes. Here's an example of one, beautiful, weird picture taken at night. They're bigger, they're more sensitive, each of them. Yeah, and they'll be on longer baselines. And on the lower left, just to show you, these are parts of the receivers being built by the company in Stellenbosch, EMSS. So it's all really happening, lots is happening, and this is, you know, there's a beautiful image of one of the MeerKAT dishes in the Karoo with the Milky Way at night, and a zoom in, if you zoomed in by, I don't know, a factor of 1,000,000 or whatever it is, you would see this, well, with radio eyes, at high frequencies, you would see this ring from that the EHT project has generated, an image of the area very, very near the central black hole in our galaxy. But in the meantime, you guys have access to one of the world's best research instruments in MeerKAT in South Africa, and I hope you get to use it over the years to come and in your careers. And thank you very much.